Thank you, sir, for the warm welcome. As you as students of engineering, particularly electronics engineering, um, uh, this group of students is going to uh, make some impact. I've seen the numbers actually. This is almost like 180 plus members joining in. This is not a small quorum. At the same time, this is actually a potential of our future in semiconductors also, which actually makes me feel very happy that okay, I'm able to share the at least my views on how the AI is actually taking over the world. What should be a electronics engineer be doing in this new era where things keep changing every few weeks. It's not even months or years. The kind of changes that we see are humongous, and I thought like this will give a this will be a perfect place to start any of the discussions, because we are in the AI era. You want it or not, but AI is everywhere today. So we need to actually understand as engineers on what is the hardware behind it. If you want to actually survive in this world where AI is changing shapes every week or every month, what should be our uh, uh, what should be our stance? How do we actually take how do we evolve as engineers, right? So particularly this is I'm glad that the EC Triple E and ECI, all the branches actually are the potential engineers who can actually go into the electronics electronics field, right? So a lot of potential which actually can help the country and the AI as a whole. Without much ado, I just proceed. This is about me. I'm Raghu Voleti. I have 25 years of experience in semiconductor field. I have led more than 25 to 30 silicons, from end to end for soft development, and then I hold around 20 plus patents, and then I work as an associate vice president in MOSCHIP Bangalore. So shifting into the agenda, we start with the introduction of why there is a dawn of AI today, why AI is booming, and we will take a look at as a slight background on how the AI started and where we are, where it started, and we see that okay, what is the scale of AI growth today? This should actually give us some perspective on how fast, as an engineer, we need to be looking at this AI as a whole, right? So that's actually the scale of AI. We are going to talk about that. What kind of data demands, what kind of computational demands that are there today, and what it means from the hardware perspective, right? And then the hardware revolution, right? Why there is a need for a AI chip, separate category of AI chips. Why are the AI chips essential, going to be essential in the future? And then what are the future semiconductor trends? What is actually going to help AI more? And then we will talk about a few real world impacts today as on today, how the applications, how AI is defining some of the applications and how it's changing the scope of some of the applications today. And at the end of the presentation, we'll actually also talk about being electronics engineers. What is your horizon? What should be your goal if you want to really contribute to the AI field through electronics? How you can do it? I have a slide for it. So with that, I'll just start. So what is AI, right? So artificial intelligence, when you see, there is actually systems are these are the systems which are trying to mimic human intelligence for various tasks, like problem solving, perception, right, decision making, learning, creating new things, right? So there is generative AI also, which I think majority of of us actually have used. Um, Pradeep sir, is it going to be interactive? Like, will I be able to? Will any student be able to,
No, sir. No, sir.
ask
It is
question?
one way only. They're listening
One
and
way
they're
only.
noting down
Yeah,
whatever
and
you're
then
explaining to them.
and
Yes.
then the questions will come later. If there are any questions here, will get later sometime.
Yeah, the
They
question
can.
and answers, pilot will be there, sir.
Okay. Okay.
So
Fine.
after your session, if at all any questions are posting by the students, you can see, sir.
Okay. Great. Great. Okay. Let me. In that
Thank
case, I'll keep proceeding rather than giving a break. Yeah.
Yes, sir. Yes, sir.
So
Yes, sir.
yeah. Yeah. So as an example, like, you started seeing the first things which everyone has started seeing in hand is like the voice assistants like Siri and Alexa. There are multiple image recognition and recommendation systems that have started coming up. And from there, you can actually see today, we can generate videos, we can generate content stories, screenplays, right? Resumes, create legal documents, you name it. AI is everywhere. Where there is any digital content, AI is there, right? So now that's actually how the AI is evolving. This actually evolves even to the point that AI is designing its own next generation of algorithms. NVIDIA today, as an example, which actually has a lot of graphics processing units based AI computations, has already announced that its next generation of AI based graphic chips, graphic control units are designed almost like 80% of the design is happening through the AI itself. So what it means is there used to be engineers who actually started architecting solutions, started coding, and then took it all through the Verilog coding and then validated them, verified them, took through the synthesis PNR and all this, the whole cycle of the semiconductors. Out of this, there used to be big teams which actually used to do this. Now the AI has entered into this end-to-end design flow, and it is doing 80% of the work. So that's actually mind-boggling, particularly for the algorithm. So if imagine it is trying to create AI is trying to create its own next gen version is like evolution, right? Human beings actually create the next generation. That's evolution. Similarly, this is how the AI is evolving today, and it's on one side it is very looks very scary, but the other side it actually gives a lot of opportunities for solving a lot of problems of the world. So any technology has this good and bad. The way the technology is used, the way the technology is mastered will make the difference. So this section, at least I wanted to make sure that we are not scared about the future of what the engineering is, but we want to engineer the future by ourselves. Right, so that's why I just thought of starting with this. Like in a way, why is the AI everywhere now? Because there is an abundant data. We are clicking pictures. You take pictures. Everyone has. Most of the people have smartphones. They actually take picture. They actually chat. They do emails. A lot of data, right? We upload specifications. We actually create presentations, including this one, right? This is all data. All this data is actually being fed to something called to a brain and a nervous system, which actually enable the AI function. And that brain and nervous system are nothing but the AI engines, right? Which are built by semiconductors at the end of the day. So we needed a deep learning algorithms and the deep learning processing, which can accumulate all the data that is created in the world and can actually make sense of the data, right? So whatever the data that is present in the internet is used as actually a training data set for a nervous system, and then a nervous system which is called actually the neural networks, and then the brain, which is actually the AI processing units. So these are all nothing but we are building the systems based on the semiconductors, the CPUs, the GPUs, the network interfaces, the storage controllers, the memories, right? So all these are fall into the semiconductors. So over the next few decades, the semiconductors is going to be the field which will change the course of technology, which will actually rewrite the technology by itself. So that's very important. So we need to understand how the future of the electronics is, what is it, what demands it is trying to meet, right? So this is what our talk is, my talk is today on. So to give you a basic overview, right, the evolution of AI concepts have started um, as early as 1950s. If you believe me, it's actually started in 1950s, right? So there is something called a symbolic AI and perceptron, which actually have laid the groundwork for the all the AI. This is in 1950s to 80s. This is where I've given on the right side, the right hand side, I can see this perceptron example, which is actually nothing but you give a set of inputs to a program, which actually multiplies the inputs with some weights. Weights is like constants, and which will get summed up. And there is a function which actually says whether the given set of inputs can match a particular criteria or not. As an example, if you are feeding a picture of a cat, to this algorithm, it will there are set of weights which actually take the pixels and create a sum and create and then there is a function which actually Q-side step function, which actually can say that this is a cat or this is not a cat. The most likely first few thousands of samples, the whole algorithm will keep failing. But the good thing that happens is it's a there is a feedback from the output to the weights. The weights keep changing as you give the output. If there is a false, the weights keep getting adjusted. And over the period of time, as you feed in lakhs of such pictures, it will actually say that, okay, if you give a cat, it will really detect the cat. If you give it a dog, it will definitely not detect it as a cat, right? So that's how the neurons are. This is almost similar to a kid who is very like 3-year-old kid who's trying to touch the fire. He touches the candle. It say the neuron says, okay, this is actually his sense organs are saying that okay, this is fire and you should not touch it. Later, he sees a glowing bulb, and when he touches the bulb is also actually something which is warm and hot. So his neurons will train him that okay, whether the fire is in the shape of a candle or a bulb or a fire on the stove or a red hot coal, you should not touch. That's how we learn, right? This is how human beings have evolved. So the basic unit, which is actually trying to create that true or false or take a decision, is the neuron in human beings. It is called perceptrons, which is actually the simplest form of artificial neuron, which was started in it's got evolved in 1950s to 60s or 70s. So that's how the concepts have evolved. And then now that you have the neurons equivalents to perceptrons, they have started building neural networks. Neural networks is nothing but it's like a simple networks of neurons that process and forward the data. So there are, instead of one perceptron, there are multiple perceptrons or neurons which actually just process the data and say that okay, this is the decision, right? So that's how the neural networks have come into the picture. And then there has been a lot of this research on neural networks, the artificial neurons, but there have been some period called periods of reduced enthusiasm, which we call as AI winters, where there is no not much research that went in. Though in 1985s, 90s, and maybe 1995s, there were actually discussions on, okay, neural networks are used for this, neural networks are used for that, but there were not so many breakthroughs in this period. That is because as with the neuron getting trained, the amount of data that the whole world is generating is not too much. So there is no data set on which not enough data set on which these neurons get trained. So the evolution, though there was internet, the amount of data that actually got generated on the internet was not so huge as much from the era where we started seeing mobile phones, cameras, and and then they're getting linked to the internet together have actually really started. There is a huge amount of data sets got created on the online, and this is where these neurons got started getting evolved, right? So the way we see today the AI, the AI's current success is not really over the past few years. It's not actually not the Chat GPT, right? So Chat GPT is not the start of the AI. AI has been there. Concept of AI has been there for past 80 years. But it got matured over the last few years, right? So because the amount of data was not so huge at that point. Today we are in that final stage of flourishing AI. So all the conditions like network speeds, storage, amount of storage that is available, the amount of data that is getting created, the kind of algorithms that got evolved, all this started actually creating that flourishing era of AI. So what are those? So you can see that there is a perfect storm here. Like, there is a sheer volume of the data has coming from the devices which are connected to the internet, right? That massive data sets have started evolving, followed by the algorithms. Like, there are many layers of neurons today which actually start creating a decision charts, right? So we actually have edge devices which make some which collect the data and which will filter the data for the first time, and then the data gets shaped, and then there are actually there are central AI machines where the stored data which is stored in the clouds get used for the training, right? So and then those training algorithms got even more mature, and then multiple layers of neural networks started actually revolutionizing the AI. Also, with that, it was not just sufficient if you have algorithms. There should be enough amount of computational power. The traditional computing is good for managing and controlling processes, running an operating system, creating nice documents, creating spawning processes. All this is good with the traditional computing system, but the major important operation that happens in the neural networks is the floats, right? Floating point operations. And GPUs, when they were used for the gaming, has a lot of these floating point operations with multiply accumulators, right? These are called tensor operations. Those operations are actually supported by GPUs by default. And instead of using the GPUs designed only for the gaming purposes, when they started using the GPUs for the AI computation, it all changed the way the AI got evolved. Then based on that, there are deep learning algorithms which actually have evolved. Along with that, there are successfully one couple of successful evolutions that have happened are convolutional neural networks, CNNs they call. CNNs are used for the image processing, right? So you give an image, you can detect whether there's a car going on, a vehicle going on. If the vehicle is moving, what is the number on the vehicle? if there is some dog which has entered a house, multiple such algorithms can be enabled with CNNs. And then there are RNNs, which are actually recurrent neural networks, which have evolved even more, which have enabled the natural language processing these days. And that's how you actually start seeing ChatGPT, even if you actually give a very informal question, it gives you a very precise and comprehensive answer. That's because it is trying to understand what you are talking. These kind of natural language processing is enabled through RNNs or transformers, they call. So RNNs, CNNs, RNNs are also called or transformers, right? So these are the things which actually have started becoming the eyes and the ears of AI. So that's how, along with the deep learning, it actually has increased the whole, whole capability of the AI engines, which are built using the GPUs, right? So the combination of the data, the algorithms, the computing power finally has unlocked the whole AI potential. That's how the AI in the world today. Now, now that we know that okay, how all this have come into picture, as we said, the graphics processing units are actually are the ones which actually started providing the flops, right? Floating point operations. Now, if you see over the past few years, almost every 5 to 6 months, the AI models and their processing powers, which is a floating point operation, has increased 2x per every 5 to 6 months. So that is humongous amount of learning and computing power that is actually being generated, right? And then if you see the amount of data today that is there in the world, it is around 181, to be precise, 181 zettabytes. Zetta is actually like a 2 power 21, sorry, 10 power 21. That's the actually amount of bytes which is actually present in the world today, and we keep actually increasing it every almost like for 25 to 30% every 2 years. And as we start using, as more people start using mobiles, as more people start using computers, as more people start using the OTTs and other digital platforms, this actually keeps even the data goes exponentially high, right? The main thing that actually is really mind-boggling is roughly 90% of the world's data has been created in last 2 years. So whatever is actually presented here is computational data, but this is the data which is used for computation. But there is a data which is actually there, the raw data, which is almost like 90% of it is got created in the last 2 years, out of which there is a filtering. There is actually some first layer of filtering and second layer of learning, and then the usable or the data which makes sense is almost like 181 zettabytes today. So that's actually a humongous amount of data that we are seeing as on date, right? These are the two revolutions. They are actually like, there is this insatiable demand for the flops. As the flops keep increasing, they keep consuming a lot of data. As much data as you actually throw into the AI engines, as much the flops increase, they get consumed that faster. So is this going to actually just grow like this? Probably yes, probably no. We will see how it goes, right? So, but at this point of time, the number of flops that is increasing is actually going even beyond the Moore's law. We'll talk about Moore's law in a few slides, but yeah, this is how it is. And then if you can see this, these two trends are really coming because of the semiconductor revolution, right? The reason why there are these many flops that we are able to supply is because those many graphic cards, those many AI accelerators are actually getting created day in, day out. And the amount of data that is getting generated is also from the electronic and digital media, which is basically running on some semiconductors. So this is in a way, the semiconductors, the amount of semiconductors, the kind of semiconductor revolution that is there out is actually pushing all this. Right, so that's a semiconductors is part and parcel, and as I mentioned in the first slide, it's like a brain and neuron of the AI. Now, as on date, if you see the kind of impacts that we have on the real world, like technology point of view, search engines, social media feeds, right, and recommendation systems like like Netflix, Amazon's, Google's, Chat GPT can also search things for you. It can give you a good it can make a good suggestion for you, right? If you are trying to go from here to some place, and then you want to have 10 different choices and budgets, ChatGPT can give it in seconds. So that kind of technology is actually driven by the AI algorithms today. Autonomous driving is completely the more the cars get automated, then the autonomous driving comes into picture. There is ADAS systems, which is actually advanced driver assistance systems. All these actually get driven by the AI. And the healthcare point of view, like image analysis, their drug discovery, personalized medicines, all these actually are getting driven by AI. They are changing. They are going to be, we will start seeing the first level of diagnostics happening through AI itself, even before we go to the doctors, right? So there will be diagnosis kiosks coming sooner or later to the complete world. And imagine having remotest part of the world getting these kiosks. That itself is like a great advantage that we can give. We can give better healthcare to many rural areas also. And that's kind of something which actually is in heavy research today, and some of it is already available in the niche markets today. To avoid any fraudulent trades based on some algorithms, right? In the market, right? Share market and all. Finance point of view, the today finance field is actually using AI to detect all the frauds. Manufacturing point of view, predictive maintenance and quality controls, and robotic operations. Like there are in Western Digital, which I worked previously. We used to have factories which we call as light dark factories, where you don't turn on lights in the factory. Everything is driven by robotics. There is one person who is keying in that I need to generate these many hard disk drives, and every operation, including the assembly of the hard disk drives, is driven by the robots. And if you go to the factory in the night, there are no lights. In the day also, day and night, right? So there are no lights fitted in that. So that's how the robotics are actually taking care of doing the complex manufacturing manufacturing tasks using the AI today. And again, the smart speakers, facial recognitions, and smart homes. This also is actually started pushing the AI boundaries even more. That's how the AI is getting adapted today. And over the next few years, I think there will be zero field, literally no field which is actually without AI. This is how it will be. Now let's look at given that that's actually the general AI overview and the scale at which the AI is growing. We'll see what it means and how the AI can be helped using the semiconductor field, right? As you know, one of the key things which actually a semiconductor engineer or the electronic engineer can actually choose is to be an ASIC engineer who does architecting logic, creating circuits, creating chips, ASIC controllers, SOCs, which can go into you name it. In every place there is a chip which actually is driving things, right? So this is a vast field. Semiconductor field is a vast field where one can actually go in and start contributing. But out of this, since we are talking about AI computing, I wanted to give a background on how AI is enabled through the compute, right? So there were CPUs, the x86 of the world, ARM architectures of the world. They are general purpose. They are sequential in nature, and then they are least efficient for the heavy AI, right? Because heavy AI requires multiple neurons to work in parallel, right? Human body is having billions of neurons working together for someone to speak, for someone to listen, for someone to see, right? So this if we want to have this kind of operations running on CPU, it's not possible because CPU has pipelines. CPUs come with pipelines. They have certain number of cores and then certain number of threads that they can run on a CPU. Usually they are actually maximum capped to 128 to 256 at this point of time per CPU, right? So there is a need for parallelism, which is only served by the GPUs. They were actually excellent starting points for AI. Especially the training algorithms got actually more matured through GPUs. Now with CPUs and GPUs having their limitation, because GPUs are general purpose, they come with a fixed way of operations. Like if you need to operate with a GPU, you need a CPU, and you need to feed the data through a particular software program in a particular fashion. It requires a file system. It requires a memory. You fill in the memory, you trigger the DMA, you get the processing done. But the era of the AI processors have actually started coming, which actually they are highly specialized, even more parallel than the GPUs, and most efficient for specific AI tasks. As an example, as we discussed, the CNN, which is actually convolutional neural network, is good for image processing, whereas a RNN is good for natural language processing. Now, a graphics card can run both of this, but there is actually some level of some level of additional logic which is not required for let's say if I'm running the the CNN on the graphics card, there is only a certain portion of the logic is useful. The rest is non-used. Similarly, if I'm running a RNN algorithm based algorithm on graphics card, only certain kind of operations are used. So the redundancy of the hardware can be removed based on application specific AI accelerators. So this is something which will start coming up sooner or later. It started coming up, but if you see today, your Apple phones, your MediaTek phones, or Samsung phones, or Qualcomm phones, they have what we call as a tensor processing units. Even Google Pixel has those, which are specialized, which are tuned for a particular kind of application, and they come in as a co-processors sitting with your main processor in your phone. So that TPUs and all actually are like the accelerators which we are trying to build for application specific purposes, right? So how will it help? Because there is no redundant logic, the amount of power it consumes is less. The amount of precision with which it can actually execute this kind of logic can execute an operation is high. So they are energy efficient and better in performance. So that's how we actually save a lot of cost when you develop a application specific AI accelerator. Okay. So that's how the AI accelerators have started coming up. And as we have discussed, like, application specific integrated circuits are like, Google's TPU as an example. And then there is a NPU, which are neural processing units, which are dedicated hardware blocks specifically for accelerating neural networks, which are actually seen in your smartphones and edge devices today. So they, as I was telling previously, they actually significantly reduce the power consumption. They are smaller, they are faster, and that's how they are actually going to gain more traction in the gaining more traction in the AI world, right? And so we can now that we have talked about this, we have talked about something called AI for so when we are trying to do look at the components, there are two things that AI purpose, the semiconductors which are designed for the AI purpose, they do two things. One is called training, another is called inferencing. We'll see what it is. So training, so there is something called AI training where you actually, the process of training begins and then there's a lot of data fed, right? There'll be the neural networks will take billions of parameters inside, and then they do the heavy lifting of uh, of training on the data being fed. As we have discussed in the perceptron model, there is a continuous learning saying that, okay, reinforced learning that will happen, which will say that, okay, you send a data to the algorithm, the output is correct, then it will get a thumbs up. If the output is wrong, it will get a thumbs down, right? So based on this, the weights of the neural networks start getting adjusted till the algorithm gets mature. So that is how the training happens. Is the biggest heavy lifting in the whole AI thing. So it is very computational intensive, and there is a power usually done through GPUs because the kind of data that you see can be either image data or audio data or something, some documents or text test data. So multiple data elements that can come in. So general purpose GPUs are used for training here mainly, right? And then from there, once the training is done, the inference actually starts. So a trained model can start. So a process of using a pre-trained AI model to make predictions or decisions is inference basically. So it needs to be highly efficient. And so what they do is, once the training is done, these weights are taken and they create the edge AI units. So based on the training data, this gets translated to smaller controllers, which are more energy efficient and faster. That's how they actually get integrated to the edge, like onto the phone or onto a kiosk or a tablet. So the prediction model starts actually prediction models actually make start doing the prediction today once the inference engines are created, and the process needs to be highly efficient. That's how they start creating application specific controllers which get deployed to the edge, and then that's how we create a specialized AI chips. So there are two types of things. One is a heavy lifting done by general purpose GPUs and compute engines, and then the AI specific controllers which actually get manufactured based on the AI inferencing requirements. So this is the two things, right? So both of these fields are actually getting more and more intense. There are controllers which actually get created for this application specific AI inferencing. If you go to Qualcomm's of the world, you will see this kind of chips getting generated, right, or designed. Now, there is one more thing that is actually there, which is driving, which is enabling, absorption of all this data that is coming in. It is not sufficient if you have data that is growing, and if it is not sufficient, if you have controllers or processing power and the chips are getting manufactured, right? Even if the number of chips that get manufactured are increasing into lakhs or billions of those chips, whereas the data is also going into zettabytes, but there should be a medium which is actually making sure that the data is taken by the chips. We should be able to bring the data to the chips, better to the computational engines. How we do it, right? So the problem with electronics is based on Moore's law. Roughly every 2 years, the amount of computation or transistor density is supposed to increase by 2x, right? So the on chip, the number of in a given chip or a given per given square the number of transistors that you see today versus a couple of years later, you will see it's actually double x, 2x, right? So it should be doubled. And though the AI and the AI inference engines are actually increasing in the compute from a compute point of view at that rate, physically to bring all this together into and assemble a data assemble the data to be taken by the CPU or the GPU or the AI processor is a challenge, because the CPU or the AI processor is ready to take the data and the data is present somewhere, but the rate at which the data is read from the storage should be increased. So for doing that, if you actually you can do that through network. As an example, I have 1 TB of data today. Within the next 6 months, it will become 2 TB, and next 6 months it's become 4 TB. So that data is increasing. So I keep adding the data storage cards, right, in a system. CPU also I can keep upgrading, right? But the bottleneck between the data and the processing element is the network through which you are actually consuming the data. So there is a network related or an interconnection between the data to the CPU or the processing power is something which has become a challenge in the past few years. Now, industry has started using some concepts which actually have started solving this. So I'm going to show you that. So this is how the Moore's law keeps predicting that, okay, every 2 years, there is a 2x of compute energy that's or 2x of transistors that you see in a given area. That's the Moore's law. This is how it is given by Gordon Moore long back, 1960s, 70s. He has given this postulate saying that, okay, he has observed that, okay, the amount of processing is doubling every 2 years. And he said it will continue this way. Now, what happens is the current semiconductor technology that we are working on is 3 nanometer and 2 nanometer. 2 nanometer is 10 power minus 9 of a meter, which is actually so small. And this is actually going to a state that, okay, you see 1 electron or 2 electrons actually in the channel, which actually go from one place to another, right? Beyond the band gap, right? So this kind of shrinking transistors size is creating challenge. So there are FinFETs, there are different technologies for all this, right? So I think you will start seeing it in your, you might have already seen it, or you might see it in the course of your next 2-3 years of your engineering, right? But what does this mean is the challenge keeps growing, right? So transistors, we are hitting a limit that we cannot shrink beyond a particular point in the transistor size. And the amount of data is increasing on the other side. And if you have to go below a particular technology, like 3 nanometer or 2 nanometer, the costs are also humongous, very huge. The challenge is getting solved as on date by something called chiplets. Sorry about that. Now, what are those chiplets? If you say this, I've just given a small example on the right side. You can see my pointer. If you can see my pointer, there are transistors, fixed number of transistors in a logic. Assume this is your tensor processing unit or a AI processor. There is a RF unit which is actually used for sensing something, sensing the data. MEMS, sorry, RF unit is used for radio, your radio portion of your controller, where you can talk to cell towers or cell towers or other radio related interfacing, right? MEMS is the sensors. Memory is where this is the DRAM, which are currently they are calling out something else. There is a new type of memory that has come, which I'll introduce in the next slide. This is like a memory, which is like your if you open your PC, you will see a DDR, right? But as the computation increases, in order to reduce the access times between the processor and the memory, we started integrating the memories onto a single package. Like if you open one of your mobile phone processor, you will see a logic die and the memory die. Minimum you will see this, right? So if you open the chip, so there is something called technology called chiplets, where different components actually, rather than getting connected through the PCB, this is your green PCB board, they actually get connected through an interposer, which sits inside a particular ASIC. So whatever you see in the interposer and above, all these get packaged through a plastic capping that you see as a chip today. If you see an Intel processor, maybe not Intel processor, in your mobile processor, if you open your mobile phone, you'll see the central processing, the application processing unit. It is nothing but something which you see like a heavily integrated circuit through an interposer like this. This is called a 2.5D packaging, where instead of let's say instead of connecting this die to this die through the PCB, there's something called interposer, which will actually route the signals from here to here. Right. So this is actually how the interposers work. This is actually called the chiplet technology. And along with that, there's a 3D packaging technology, which will make this shrink this die even further. Let's say if I can stack the memory die over the logic die, and the MEMS and the RF over the memory die. This will actually come in a smaller package, but how do you route the signals? For routing the signals, there is something called through silicon vias. Through silicon vias is a technology where you provide some through the silicon, you provide routing tracks from one chip to another. So this technology is also going to actually increase the density of the computation. Okay, sorry, just give me a second. Yeah, sorry, come back. So what will actually help is by doing this, the connectivity between the chips is now also in terms of nanometers, which implies the latencies get reduced. The interface can operate faster. You can actually send more data from the memory in parallel to the computation element, like the AI engine, right? So this is helping in reducing the power consumptions, because the longer the routes, the more the repeaters that are required on a particular track, which will start increasing the whole power. So for that reason, there is advanced packaging technologies are being employed today. So chiplets and advanced packaging is enabling enabling us to increase the density of the processing in a given area. So that's how the technology is helping. The other major thing is having a memory which is energy efficient, right? And then overall energy efficiency of the chip, right? So memory is the bottleneck. As I was telling, though there is a data, though there is a compute enough AI processing power, unless this data is sent uh, at a faster rate to the compute element, it will not be able to output the decisions at that faster rate, right? So they say that okay, that strength of the chain lies in the weakest link. So the fastness of a processor lies in the slowest of the uh, slowest of the pipeline stage. So the memory, if it is slow, the processing output will also be slow. For that, there is a new technology called high bandwidth memory. HBM memories are actually coming up very rapidly today to enable highest and fastest processing for the data. So it provides data accesses at a very high rate, and which will actually help in processing the data more thoroughly and more faster, and creating more number of flops, enabling more number of flops for the AI processing. Right. The other thing is that more the compute that we do, the more the power consumption that we have. Today, as an example, the biggest of the supercomputer today requires almost a nuclear reactor worth energy or power that to drive it. So the energy efficiency is going to be a very critical, because there is a finite energy in the whole planet, and we can supply the compute with a finite amount of energy. So for that reason, there are multiple things that we do often in the controllers today. We do something called voltage scaling. We do dynamic voltage frequency scaling that we do. These kind of technologies, design methodologies are helping in reducing the total power. Okay. Now, how are the AI applications impacting the whole industry? How the industry is changing, right? If you see on the device, AI for camera processing, facial recognition that we have seen in the previous also we discussed about it. Similarly, IoT devices, like there are devices like smart sensors, smart home sensors, industrial sensors, wearables, factories, your transport tracking, all this actually are I fall into IoT devices, right? And autonomous vehicles are, as we discussed, is there are multiple very varied applications which are there inside one car itself. There are almost like 18 to 20 processors today in some of the cars today, and it's going to go to 100 processing units in a car. What we drive is no more a normal car, right? We are driving 100 computers together. That's how the cars will be in the future, near future. It's not something beyond 10 years or anything. You will start seeing that in the next 6 months. And then these are on the edge. And then the data center AI, which is actually required for complex generative AIs like ChatGPT, Gemini. All these engines actually start using data center class of computations, which will start creating the content as we actually start asking for more. So this is where the data centers are the places where you actually enable a lot of training for the next generation AI models. As I said, AI itself started impacting the semiconductors. Today, as I said, the AI algorithms based AI units, some of the AI units which NVIDIA is preparing, more than 80% of the work is done by the AI agents. So AI is used for today detecting the defects in the in a chip. So yield improvement is one more thing. Like yield is like you manufacture 1,000 dies. Out of the 1,000, how many of them are functional? If you have to understand that, you need to do some testing and your wafer level testing. And if a particular die is not passing a test, you will throw it out. So let's say for 100, only 80 dies are actually working. For every 100 dies, the only 80 dies are functional. The yield percent is called 80%. Now to understand which particular process in the manufacturing is causing faults in this 20 dies which are being thrown out, and how to mitigate it, how to improve that 20% to only 2%, like how to take the yield from 80% to 98%. These kind of analysis today people are doing with using the AI tools and AI processing, right? So these are actually going to be only a few, very few. I just try to indicate things which are being used for the semiconductor purpose only, right? So so this is how the whole AI roadmap is looking like, right? Now, what are the other technologies which can actually start changing the whole picture of the AI, right? We have already seen that there is a high performance memory that we have that is coming up, high performance package technologies that we started seeing, AI application specific AI accelerators that we started seeing, usage of AI in helping the semiconductors itself we have started seeing, right? So it will increase the quality, it will increase the yield, it will increase the outcome, right? So this is all good, but what else are the things which are not on the above the horizon? Like usually you see things, these are things which are noticeable, but there are research fields which we don't see. I have just captured them in the next slide, which is actually currently there are three different things which are happening. One is rapid advancements in the AI hardware architectures. Like there are different models having different architectures. Till I don't know how many of you have seen something called DeepSeek coming from China. Till DeepSeek has come into picture, the NVIDIA's GPU demand was X. Let's say if you have to build a AI application, or if you have to build a AI based processing element, the number of flops that were required were X before the DeepSeek has come. The DeepSeek has changed it to X by 2 or even X by 4 in some cases. So the algorithms, the kind of architecture that AI is bringing in, the changes that the AI hardware architectures are bringing in, is changing the way the whole demand on the semiconductors and the kind of semiconductor that you see is going to change based on the hardware architecture changes, the algorithm changes, right? So there are rapid advancements that are happening here. Then there are new types of materials that are being explored. As an example, there are gallium oxide based research that is going on to see silicon today, since we have reached to nanometer level, and then there is a beyond that 2 nanometer, 1 nanometer, it's actually very difficult to shrink it further. That's why we are trying to look at materials which are other than the silicon dioxide, right? So gallium oxide, carbon nanotubes, graphene and 2D material, these kind of multiple such things are being actually looked into, which will actually start changing the course of how the semiconductors will be in the next few years, right? If one of this, if the, let's say gallium oxide is actually going to be front coming up to the market level, right? Commercialization level. then the way you design the chips will change. So electronic engineers should actually understand this, right? Say today till date we are talking about silicon oxide, right? Silicon dioxide. Silicon is the place where we are actually based silicon based gates are what we are using today. But if the materials change, the way you design a gate changes. The way you actually synthesize, implement these logic changes. So any new material coming in will change the way an electronic engineer will work on or a semiconductor engineer will work on. So this is something to take a look at. Keep a tab on it. Keep following it. Right. Look at what kind of new materials coming up. Neuromorphic computing is completely different. It's like rather than taking a digital 0-1 kind of a decision, this is like mimicking a brain like synapses for ultra low power AI inference. Like these are event driven computing with which can actually reduce the total CPU power consumption to less than 1% of what they are using today. So these are kind of deep research fields which are happening behind the curtains. We'll start seeing this, and who are driving all this is like MIT, Stanford, all these academic labs, and then industrial R&Ds are also doing. IBM research has it. Samsung has Samsung Institutes of Technologies have it. TSMC, IMEC. Some of these are the places where this research happens. I'm just giving you some of this because this could be your next pursuit, right? Also, there are many government-backed programs like USA. There is DARPA. Japan, there is something called RIKEN. Europe has a European graphene flagship as an example. Those kind of different forums are there where a completely different kind of research is happening to find an alternative for silicon. And that will any of this getting clicked will actually change the whole landscape of the semiconductors, right? Now, that being the background, you as electronic engineers, what kind of roles that you can take to be part of this whole AI revolution as it grows, right? Chip designing is a great place. Chip designing, digital, analog, and mixed signal circuits designs, right? This is one great place. Packaging and integration. This is as I said, the 2D, 3D packaging, 2.5D, 3D packaging. These things is actually also is going to grow. Verification and testing. Out of all the flow, right? Verification and testing is very critical. Imagine an autonomous vehicle in which someone has forgot to write a test for a chip, which is in the braking system. In a corner condition, if the brake doesn't work, that's it. You will be costing a life. So verification is going to be very critical, and quality assurance for this through testing, right? Once the chip is back, you test it from the quality point of view. That's very important. So engineers with verification capabilities and knack for verifying things, right, are very key. Embedded systems, like integrating hardware into different types of devices. This is also very niche. Going to be even more. It's not very niche. It's very common, but going to become very niche skill going forward as the AI keeps increasing and AI keeps coming into the edge. It's the embedded system engineer who needs to understand these algorithms and start putting it into the smaller and smaller device. So embedded systems is also going to flourish, right? And the research and development, as we discussed, innovations in the hardware, right? And pushing the technology boundaries for the sake of lesser power, higher performance, lower cost, right? Lower energy. All these are actually going to help. So these are the kind of jobs that you start seeing, which will grow as the AI comes, right? And all this is actually in the hands of electronic engineers. So you choose a great field rather than just going behind the first salaries, right? People have people think that, okay, I have exited my college with this kind of salary, right? That's not what matters. what matters is, will that salary is landing you in any of these kind of jobs. You are in a core electronics field, you better actually take this opportunity which is at hand, right? So there is a AI revolution that is going on all around, and I hope this has given you a good overview of where you can land up and how you can actually build your career around the AI. With that, I will conclude. If you have any questions, I'll be happy to take. If not, thank you.
Sir, thank you very much, sir, for your session. I have already, dear students, I have already enabled the Q&A palette. So if you have any questions to ask to the expert today, you can feel free to post the question in Q&A. Raghu sir, it seems no questions are asked by the students. Sir.
Okay. Thank you. Thank you, sir. Thank you, Srinivas.
So
Sir.
On behalf
you,
of
sir.
all the students and organizers, I extend our heartfelt thanks to you, sir.
Thank you, sir.
For delivering such an insightful and engaging session on the cutting edge technology, sir.
Yeah.
So thank you once again for taking the time to enlighten us, sir. Thank you. Thank you very much.
Thank you, sir. All the best. All the best. All the all of you. Actually, I think
Yep.
in all these branches are connected to the electronics, ECE, EEE, and ECI. I think this is going to be a great field, right? So please.
Thank you very much for your concern.
Yeah, Raghu sir. Yeah, sir,
sir.
Raghu sir. Yeah,
Sir.
myself, I'm Dr. Venkateshwar Reddy.
Sir, I think
Hi, sir.
Venkateshwar Reddy sir is also there in the list.
Yeah,
sir.
Associate Professor and Head Department of ECE, sir. And we are very fortunate and we are very thankful to you, sir, for accepting our, for taking a wonderful session, sir.
Thank you,
And
sir.
yeah, you have given a wonderful session, sir. You have touched upon artificial intelligence and advancements in artificial intelligence and how AI is revolutionizing the semiconductor industry and advancements in semiconductor industry. And also you have touched upon the what are the new material that can come up that can replace silicon for manufacturing the semiconductors, and also what are the various job opportunities for electronics communication engineering students and electrical engineering students and ECA students, sir. And really we are very thankful to you, sir, for from all the fraternity of Kids Warangal and from the on behalf of all Kids Warangal and fraternity. And sir, I would like to tell you, sir, this is a 45 years institute, sir, Kids Warangal. Raghu, sir.
Great, sir. Great, sir.
Yeah, 45 years institution, sir. And recently we have revised the this curriculum, sir, under ERR 24, sir. In that ERR 24, we have incorporated this expert talk series session. So that various experts from other experts from industries will are going to deliver the lectures under this expert talk series, sir. And so that it will bridge the gap between the students and the gap between the industry and academics, sir. And thank you very much, sir. And we are very much thankful to you, sir. Really.
Thank you. Sir.
We are very much thankful to you, sir. Thank you, sir.
I hope it helps. It helps. I think. Yeah. I would be actually
really,
happy
sir,
to.
Really.
I'll be happy to get any feedback if there is some more details are required. Chandrasekhar, Dr. Chandrasekhar is my my batchmate. Yeah, we are good friends. So
yes, sir. Sir is also there in the meeting, sir.
Yeah.
Yes, sir. It's a wonderful session, sir. Thank you, sir.
Thank you, sir. Thank you.
Sure, sir. We'll be collecting the feedback from the students also, sir, in due course of time.
Sure. Thank you.
Thank you very much, sir.
Bye.
Dear students, it is the time to write the test. So I'll be providing the test link here in the chat box. And the test is already provided to our WhatsApp group and also through mail. So let me provide the same test link here also for your reference. So test link has been posted in the chat box. So try to click on the link and read the questions carefully and fill your details first before you write. And your time is only 10 minutes.